Hello everyone, thank you for joining me today as we discuss logarithms and their graphs. We have two objectives today. We are going to recognize logarithms as inverses of exponential functions. We will also evaluate some logarithms and sketch a few logarithmic function graphs. So what are logarithms? Well, previously, we've worked with exponential functions, where we're given a base, we're given an exponent, and we evaluate that to get the value. For instance, here, 9 to the power of 2, 9 is the base, 2 is the exponent. That gives us a value of 81. Well, in some instances, we know the base and we know the value, but we want to know the exponent. Like here, 9 to what power equals 81? Well, we know that that power is 2. We just answered that. But in that situation, we are doing exponential thinking in reverse. In other words, we're using the inverse of an exponential function, and that's exactly what a logarithm is. So down below, you can see an example of a logarithm that would read as log base 7 of 343, and that is equal to 3. Log base 7 of 343 equals 3 because to go from a base of 7 to 343 using an exponent, the exponent needed there is 3. 7 to this power gives us this value, and that's the mechanics of how logarithms are written and what they're asking for. So let's practice those mechanics a little bit more. On the screen here, you can see some examples of exponential functions and then, equivalent examples of logarithmic equations. Here, 5 squared equals 25. That's because 5, to the power of 2 equals 25. So here, when we rewrite that as a log, 5 raised to this power gets us this answer. Similarly here, 4 to the power of 3 will give us an answer of 64. 7 to the power of 0 results in a value of 1. And again, down here, 7 to the power of 3 equals 343. Let's practice those mechanics by going back and forth between exponential form and logarithmic form. Starting here, write each equation in logarithmic form. Here's 2 to the power of 5 equals 32. Well, recognize that 2 is the base, 5 is the exponent, 32 is the value in this situation. So in terms of writing this in logarithmic form, we would say log, L-O-G. The base here is 2. That's like a subscript number, a little bit smaller down below. The value we're getting is 32, and the exponent we need to get that value is 5. So there it is in logarithmic form, log base 2 of 32 equals 5. Picking up the pace a little bit here now. Here, 1/3 is our base, so we will say log base 1/3. The value we're getting out of this is 9, and the exponent we need to get that value is -2. The answer to a logarithm, the value of a logarithm is the exponent in that situation, in this case, -2. One more here, 4 to the power of -1 equals 1/4. Well, 4 is the base, so we'll say log base 4. 1/4 or 0.25 is the value we're getting here, and we're getting that value using an exponent of -1. Let's try that here now in reverse. So here we'll start with logarithmic form and we'll rewrite in exponential form. Well, here 4 is the base, 256 is the value that we're getting from that, 4 is the exponent that gets us that value. So here 4 is the base, 4 is the exponent, 256 is the value we get from that. There it is in exponential form. Here 1/3 is the base, -4 is the exponent that takes us to a value of 81. Here, this one's interesting because the base is not explicitly written. Well, in that situation, we have on our hands here what's called the common log. This is a log that's used more commonly than others. And like we like to take shortcuts in mathematics, this is a shortcut we take by not writing that base. Kind of like how we don't write an index of 2 for a square root. We assume that to be a square root, right? Here, this is log base 10. So our base is 10, our exponent is -3, and that gets us a value of 1/1000th. Well, now that we've practiced the mechanics of how to write logarithms, let's actually evaluate some of our logarithms, which is one of our objectives for today. Let's start with log base 5 of 125. There is a way to do this on a calculator, but we'll practice here doing some mental math. So remember what this is saying. This is saying our base is 5, the value we're getting is 125, and this logarithm is asking for the exponent to get there. Well, 5 cubed is 125, and so our answer here is 3. Down here, what exponent do we need to take a base of 13 to a value of 13? Well, that exponent is 1. Here, remember our base is 10. Well, if our base is 10, how do we get to a value of 100? Well, we do that by doing 10 squared. 10 to the power of 2 is 100. Here, our base is 2, our value is 64. How do we get there using an exponent? Well, it may take you a little bit of mental math potentially, but 2 to the power of 6 is 64. Here, our base is 6, trying to get a value of negative 36 using an exponent. Well, even if you think to try negative 2, a negative exponent just tells us to do a reciprocal. So 6 to the power of negative 2 would be 1 over 36, but that's not what we're trying to get. We're trying to get negative 36. And as it turns out, there is no exponent you can use to turn a positive base into a negative value. And so this expression here is undefined. We'll talk more about this later, but negative numbers are not in the domain of such a logarithmic expression. One more here, our base is 25, trying to get a value of 5. Well, it's interesting that our base is bigger than our value, but recall from earlier discussions that 5 is the square root of 25, and we can apply a square root using an exponent of 1/2. 25 to the power of 1/2 is equal to 5. Therefore, the value of this logarithm is 1/2. So at this point, we've talked about what a logarithm is, we've talked about some of the mechanics of logarithmic expressions, and we have now evaluated some logarithms. We're now going to switch gears and think of logarithms more as functions. And here, we'll start by connecting the fact that logarithms and exponential functions are inverses of each other. So consider y equals log base 12 of x. Let's find the inverse of that function using the same process we've discussed previously, by switching x and y, and then solving for y. Well, solving for y here is something we maybe haven't done yet, but we can isolate that y if we rewrite this in exponential form, where 12 is the base, x is the exponent that gets us to our value of y. And so our inverse now, if the original function was named f, would be 12 to the power of x. Log base 12 and 12 to the power of, those are inverses of each other. Hope it's not too much of a stretch for you to understand here then that the inverse of log base 9 of x would be 9 to the power of x. So it's true that logarithmic functions and exponential functions are inverses of each other, and that's a technique we can use to graph logarithmic functions. We're maybe not as familiar with logarithms yet, so plugging numbers into logarithms and picking the right numbers that result in y values that are easy to graph might be difficult for us. And so we're going to start graphing logarithms using this technique here, where we have graphed exponential functions before, so we'll graph the exponential function first and then recognize that the logarithmic function, being its inverse, would just switch the x and y values, reflecting across that diagonal line y equals x. So let's do an example of that. We're going to graph y equals 3 to the power of x and its inverse, log base 3 of x. We'll do that on the same set of axes here. So I'm going to try to pick up the pace here a little bit. If you take each of these x values and plug them into the 3 to the power of x, these are the y values that you'll get. So let's go ahead and plot those points. Plotting those points in blue here. These fractions I'll kind of estimate the best I can. And remember, this exponential function showing that increasing rate of growth has a horizontal asymptote right here at y equals 0. So we should draw it in such a way that it doesn't ever touch the x-axis. This is 3 to the power of x. Now to graph log base 3 of x, we're maybe not as familiar with logarithms yet to pick our own values and plug them in and get results that are easy to graph. And so that's why I thought it would be helpful to graph its inverse first, because now we can just take those x's and y's and flip them around. And now I can plot these 5 red points, starting with 9, 2, here's 3, 1. Now I'm going to stop reading them out loud. But you can see that when we connect these points now, we get that symmetry across that diagonal line y equals x. And whereas the blue exponential function has a horizontal asymptote at y equals 0, the red logarithmic function has a vertical asymptote at x equals 0. And that goes hand in hand with the fact that a function and its inverse will switch domain and range. The domain for this exponential function is all real numbers. The range for its logarithmic inverse is all real numbers. The range for the exponential function was y values greater than 0. Well, you can see from the graph that the domain for its logarithmic inverse is all the x values greater than 0. We'll finish today with one word problem just to show the applications of logarithms in the real world. And this application is the pH of a substance. So the pH of a substance is given by the formula negative log of H+, where H+ is the concentration of hydrogen ions in that substance. We're going to take the 5 substances below. We're going to find the pH of each using this formula right here. We will then use that to determine whether each of those substances would be categorized as either being an acid or a base, where 7 is considered to be neutral on that pH scale. Now, I'm not going to show every single calculation here because this is a video trying to keep it somewhat short, okay? But let's start with baking soda here. We have the concentration of hydrogen ions given to us in scientific notation here. This is just a really small decimal. Okay, we have to plug that into our formula that I circled in red up above. So we have to do negative, and this is common log now, log base 10. There's a button for that on your calculator. And inside of that, we're doing 1.3 times 10 to the power of negative 9. That's going to spit out a number for us here, and the number that it gives us is 8.9. Baking soda would have an 8.9 on the pH scale. Anything greater than 7 is considered to be a base, and so we will call this a base, and I'm going to abbreviate here with a capital B. You're welcome to pause the video before I spoil all the answers here, but I'm going to spoil them right now. When you plug in the rest of these are the pH values that you get. I'm not writing down every single calculation. I'm not showing the calculation. You can find the common log button on your calculator. It's literally log. These are the pH values that we get. So lemon juice is rather acidic there, pretty far from 7 on the pH scale. Coffee, not quite as acidic, right? Soda, a little bit more. Bleach is very basic, right? My understanding is the further away we get from neutral, the more volatile a substance is, the more dangerous it is. That's why we don't mess around with bleach or perhaps baking soda, things like that. Got to be careful with those. The purpose of this was to show an application of logarithms. Here it is, used to calculate the pH value of a substance. So that's enough about logarithms for now. Thank you for watching.